So welcome everyone. We are now in week number 12. We're really coming to the end of the semester. It's very sad for all of you. Never sing me again. I know it'll be tough. I think you guys can pull through this one. I really do. I have faith. I have faith. But until then, we are now going to the next chapter. I'm going to share my screen here, and we are going to do the chapter on regression. So chapter 15 is a lead into 16. They're very much correlated, no pun intended, or was there? I don't know. Actually, I do. There was. But anywho, so I'm not sure what that meant, but okay, fine. A nice emoji. So we know from chapter 15, which was on scatter plots, that when you're dealing with two quantitative variables, you think there might be some kind of connection between them. You make a scatter plot, it looks linear, and we have this line that we draw through it, which kind of is the best line that we can draw. And we talk about whether or not it's linear, whether it's positive or negative, how strong the correlation is, whether or not there are outliers. This chapter is about finding that line in the first place and what that line means. So regression in this context, as the first paragraph says, a linear association between two variables can be summarized by drawing a regression line on the scatter plot that fits the points as well as possible. Now, the question, as well as possible, what does that mean? There is a very specific mathematical way of finding that line. Your calculator can do it. Excel can do it. I'm sure pretty much you could just do a regression calculator Google search and they can do it. I'm sure you'll find a link that can do it. The formulas are a little complicated, not horrible, but a little complicated. So that's why we have technology to do it for us. But regression is essentially, at least in this level, finding this line based upon the data. Obviously, we all agree, I would hope, that this line does not fit the data very well. I think we can all agree on that. But if someone else were to go ahead and draw that line, then I can't by eye say whether or not one is better than the other. They're virtually identical. They have slightly different slopes and slightly different y-intercepts. So how is it that we can find the best line? Again, you don't do it by hand. There's formulas for it, or you let the calculator do it. Calculators can do a lot of amazing things very quickly that human beings don't really have the capability of. So let's use a line to make a prediction, because at the end of the day, why do we draw this line? We draw this line to make predictions, as we're going to see in a second. So class activity. How well can you predict the size of a person's hand if you know their height? Spread the hand you don't write with, your left hand, I guess, or most people, as wide as possible and measure the distance from the tip of your thumb to the tip of your pinky. We're not actually going to do this activity because we don't have a group of people to do this for. We don't have rulers. So let's, ignore this one. And let's see if we can find a better one. Yeah, so essentially this first one, we can't really do because, we don't have rulers for all of us and so on. But we can at least go through it conceptually with what did Tolaire say? That's funny. But humans created the calculator. That's true. We did create the calculator to do things that we can't do ourselves, or that at least will be too difficult for us to do ourselves. But you are right. Humans did create the calculator. But who created humans? Maybe it was maybe we're like in a matrix simulation, and really, it's like a big calculator. And in the calculator, we invent calculators that in themselves, well, it's like a never-ending sequence.
That's like what came first, the chicken or the egg?
Well, if you have to ask. Okay, anyway, so class activity. How well can you predict the size of a person's hand and their height? So we spread it as wide as possible, and we're going to write the distance down. So we all do that. Okay, so let's suppose we all do that. We're not actually going to do it. You can raise your hand all you want. Yes, question?
I got 21 centimeters according to this.
Oh.
can use that.
You can have to do it. Oh, 21.
Centimeters.
Oh my God. Okay, I got a small hand. Okay, so suppose we all do that. Suppose we all go ahead and we do our height and we do our hand span, and we get a value, whatever it is. Okay, now we're not actually going to do it because I don't want to. But essentially, here's what happens. Okay, suppose this is the equation that was calculated via a regression analysis that we are going to get into in a few minutes. So perhaps, or somehow, this is the line that we know to be the correct best line. The question says, what hand span does the equation predict for a height of 68 inches? Well, all you do is you plug in 68 inches into the calculator. So negative 5.6 plus 0.4 times 68. It predicts a 21.6 centimeter hand span. Hopefully you did the math in your calculator and got the same answer. So where am I going to make a dot? I'm going to go to my scatter plot and go to 68 inches, which is right here. And the line predicts 21.6. So I'm going to make a dot. I don't know how to do that. I'm going to make a dot right about there. It's probably a little too low. Hold on. Let's try this again. Here's 20, here's 21 right in the middle. So I would say about there. That is the predicted line, the predicted hand span according to this equation. Again, I don't know if this equation is true, but it's the one that was calculated. Okay. It says graph the regression line. Okay, let's graph the regression line. We have 1 point on it for 68 inches and therefore 21.6. To graph a line, how many points do we need? We need 2. So let's predict for 74, negative 5.6 plus 0.4 times 74. That predicts 24. That's a nice, wonderful number because that's exactly on the line. So it's easy to write. So the best fit line would look something like this. Does that seem reasonable as the best fit line for this data?
I guess.
I don't know. I mean, more dots are beneath it, but you have that dot way above that might bring it up. Hard to say, but hey, it's what was calculated. Now, quick question for you. What is the y-intercept according to this equation? Right, this is my y value. Here's my x value. What is the y-intercept?
Don't you have to graph more of the line?
No,
Oh, no, wait, never mind.
What's the form of a line? Y equals, what's the generic form of a line? Y equals?
MX.
mx plus b.
Mx plus b. Now they put the order differently. They did b plus mx. That's okay. So what does the m stand for?
Slope.
And what does the b stand for?
The y-intercept.
The y-intercept. So again, I ask, what's the y-intercept?
Negative 5.6.
Negative 5.6, which if you have, I mean, let's think about what that means. That says that if you have someone who's 0 inches tall, their hand span will be negative 5.6 centimeters. So that obviously makes no sense, right? So why does it make no sense? Because remember, don't extrapolate your data, your line outside of the range of data. This data was collected, collated, I guess, whatever the word is, for people with what heights, from what height to what height. Based upon this scatter plot, what's the lowest height and what's the highest height?
62 to 74.
62 inches to 74 inches. So you can't assume that the trend continues indefinitely, right? Which is the danger of taking your best fit line outside the range of data. In addition, there's another issue. It kind of looks like the y-intercept should be about 19. So what do they mean by the y-intercept of -5.6? It kind of looks like, I mean, I deliberately led to the line early. I didn't want to go all the way because it looks like it should be about 19. So what happened there? Who can see it? Who can see it? The answer's on the page. Who can see it? Sorry if I look at my phone. I'm waiting for my family got exposed, so they're getting their test results. So every time my phone goes off, I just check it. Hope you forgive me. So the answer is that look at the scale. It doesn't go to 0. The scale goes 62, and then this is like what, 60 maybe? 61? I don't know, whatever it is. Right?
63.
The scale's off. So don't assume that the vertical scale and the horizontal scale are aligned. Right? In reality, this thing should be way further to the left to accommodate these being so high. Right? Which is the danger. Usually what we do, we like to draw these little things here to indicate that the line is not starting from 0. They're just kind of like a gap. And then it starts from some number. But in that sense, you know, this would be okay. Just don't interpret the, once again, don't take the line past the data points. That's basically what it comes down to. Okay, which is kind of why I stopped it. Actually, it's exactly why I stopped it. Okay, add a point for, we're not going to do that. Okay, now, so Solaire, you did one, correct? We're going to use yours just for the sake of an example. How tall are you, Solaire? In inches.
In inches, I'm 5'6".
Okay, so you're 66 inches. And what was your, huh?
Yeah, sorry. Yeah.
And what was your
21.
Right,
Centimeter.
21. Okay, so this was here. And you got 21, you said. So your value was basically close to the line, but not quite on it, it looks like. Agreed?
Mm-hmm.
So how far, if I were to zoom in on this point right here, if I were to zoom in, what I would see is essentially something else like that, right? I'd see a point above the line. And the question is, what is this distance? What is, as they say here, the actual minus the predicted? Okay, the actual was how much again?
21.
21. That's my actual y value. But what is the predicted y value? How do I get the predicted y value? Well, that's what the equation's for. When I plug you in, -5.6 plus 0.4 times 66, I get 20.8. So that means that the predicted, what the line says it should be, is 20.8. So what is your actual minus your predicted? It's 0.2. We call that the residual. The residual for that point, because every point gets its own residual, the residual for that point is 0.2, because the actual minus the predicted is 0.2. Your actual height is 20, the actual handspan is 21. The predicted, if the line was valid, is 20.8, and therefore the residual is 0.2. Every point on the scatter plot has its own residual. Does that make sense?
Yes.
Okay, we just calculated yours, but every point gets a residual. Okay, if your residual is a positive number, that means the actual is more than the predicted. It means you're above the line and your handspan is larger than the average for a person with your height. So there, you're better than average.
Woo.
But not that much better.
Aw.
Yeah. If your residual is negative, then your handspan is lower than average or less than average for a person with your height. And if your residual is 0, your handspan is average for a person with your height. Okay, so let's not worry about that. Okay, so now let's actually go ahead and see how we can actually create the best fit line. In this section, you will learn the method that software uses to get the regression equation. So use this scatter plot to think about the following methods of constructing a summary line. A student suggests that the best line is the one that goes through the most points. Draw this line or lines in the plot. Give me, I mean, how many points is it possible with this scatter plot for a line to go through? 2. It could be that. That goes through 2. It could be that. It could be that. It could be that. It could be that. Or it could be, oh crap. Oh, let's undo that one. Or it could be this. What do you think? What do you say looking at the 4 original points, which I'm going to darken? The point right here, point right there, point right there, point right there. Would any of these lines in your experience be the one that best fits all 4 lines?
Nah.
Nah. To be honest, if I wanted one that best fits the 4 lines, I would do something like maybe something like this. What do you think? When you look at those 4 dots, would a line like this be the trend as given? I don't know. Hard to say, but it just shows you that the whole goes through the most points thing doesn't work. That's not what we're going to be going for. Okay, so the whole try to get it to the most points, that's not how we do it. And that's not how software does it. One student suggests the best summary line is the one that has half of the points on one side and half of the points on the other side. Well, how many lines could you draw that have half on one side and half on the other side?
1,
2.
Really?
2, wait.
2.
2? I don't know. How about this? Does that count?
Yeah.
How about this? Does that count? Does
Yeah.
that count?
Okay.
Does that count? Does that count? Does that count?
Yeah.
What am I getting at? How many lines have half on one side, half on the other?
Like 8.
A lot.
A lot. 8. I can draw more. I can keep going.
Oh,
Doesn't
you
stop.
have more, but on the page so far you 8.
100%. But I'm saying in general, how many lines are there that have half on one side, half on the other?
Several.
Several. Can we be more specific than several?
An indefinite amount.
An indefinite amount. Indefinite just means we can't calculate it. But let's go one step further and say an infinite number. Sorry, I'm here to teach you English as well. When you leave my class, you will speak English much more goodly than you do now. Okay, so there's an infinite number of lines, so that's not it either. That doesn't work either. A student suggests the best one is the one that makes the errors in prediction, i.e. the residuals, as small as possible. In other words, if you make a line, let's say I just draw a random line here. Oh, I didn't mean to stop. Okay, let's say I draw a random line here like this. That's a horrible line. You know why it was a bad line? Because it wasn't a line. Okay, let's say I draw this line right here. And I said, what are the residuals? Well, this distance here is 1 residual. The distance from the actual minus the predicted just beneath it. This one here is negative, but we take the absolute value, that makes it positive. So that's 2 positive numbers. And then I have this residual here, and then I have this residual here. So one student says, add up those 4 numbers. Now, if I were to go ahead and make a completely different line like this green one here, and I said, no, that's the best line. Well, that line would have its own 4 residuals. And I say, whichever of those 2 lines has the one with the lowest sum, that's going to be my best fit line. What do you think of that idea? Take the line with the smallest sum of your residuals.
Wouldn't it be the same for both lines? Because if you're moving the position of the line, you're taking less residual from one and adding it to the other. Or no?
Well, that would certainly be true if they're on top of each other, like they are here. But if I have points that are just randomly located, I don't necessarily know if that's going to be true or not.
Okay.
I mean, it's definitely true here, because if I remove from here, I gain from there and vice versa. I agree with you. But I think in general, I don't think in general that would be a true statement.
Okay.
Okay. So this idea is pretty good. This idea is pretty good. It's not the best idea. but it's pretty good. Okay, and it could be that the reason why it's a problematic is because of Tulaire's idea that however you do it, the sum of the absolute values will always add to the same number. That might very well be the case. I don't know. I have to really think about that one. I'm not sure if that's true or not. I don't know. It's certainly a good something I should look into because I just don't know. The reason I don't know is because I know what we do and it's not this. Okay. And as such, there's got to be something wrong with this one. I just don't know if that's the reason or not. I never really thought about it. But the last suggestion seems plausible and reminds us of the MAD, right? To take the sum of the differences and divide by how many there is, right? So very similar. The only difference is we don't divide by n, but that's okay because we all agree how many points there are. So we'd all divide by n, no matter what line we picked. So in reality, it's like we're taking the MAD. So let's actually see what happens here. It's clear what the best fitting line for these data is. Draw it. Oh, it's clear, huh? I don't know if it's clear, but okay. I think he wants halfway between those points, halfway between those points, and then connect them with a line. I think that's what, the clearness is. So assuming that's true, then we have these 4 points, 2, 3, that's the one down here, 2, 7, that's the one over here, 8, 5, and 8, 13. So what is the predicted value if this is truly the line, which is halfway between these two numbers? Halfway between 3 and 7 is 5. What is the predicted value for 2? It's going to be 5, what the line gives you. And how about this one? What's it going to be? What's the predicted value going to be?
Sorry, can you go over that one more time?
Sure. This point down here, its predicted value is what the line is right above it, which is 5. What is the predicted value for this one?
Oh, it's still 5.
It's still 5. And what about this one, 8, 5? What's the predicted value there?
Well, we could say 9.
Yeah. Okay. So the predicted value, sorry, the predicted value is 9. I was already subtracting. The predicted value is 9, halfway between 5 and 13. And how about this one here? What's the predicted value?
Same.
Same. So what's the residual here? Actual minus predicted is how much?
Actual minus predicted.
Is that the actual y minus the predicted y?
Yes, the actual y value, x is just the location. So the y
right.
values.
Well,
So-
2.
3
Negative.
minus 5, -2,
-2, and this one is going to be +2, and this one's going to be -4, and this one's going to be +4.
Okay.
And when I absolute value them all and add them, what do I get? I get 12, right? 2 + 2 + 4 + 4. I get 12.
I'm
Okay.
sorry, I don't know if I'm blanking or not, but can you do the math part of that?
What's the absolute value of -2?
Are we plugging in?
You're taking these
Wait.
numbers, your absolute value in these 4 numbers and adding them.
Oh, okay, I see it now. Never mind.
Okay, so 2, 2, 4, and 4. So we got, for this line, we got a sum of these of 12.
Professor,
Yes.
how did you get the predicted y, the 5599?
The predicted y came from the line. If the line is your best fit, so the line is the best predictor of data, that means whatever x value you have to get the y value, you go up to the line or down to the line, depending on where you are. So for an x value of 2, I predict 5. And for next value of 8, I predict 9.
So like an example, I guess,
Yeah.
what I'm seeing is if you took the average of the left 2 dots like you did, where it's like 7 + 3, which is 10 divided by 2 is 5.
Yeah.
And then the same for the right, and that would give you the best predicted line?
Yeah.
Okay.
Well, no, that's this guess for the line.
Yeah, predicted.
Yeah, that's this guess for what the best line should be.
Okay.
So we got a sum of 12. That's what we got when we did it this way. Okay. So now let's do it again and take a completely different line.
Professor,
Yes.
I'm sorry. Can you go back to the previous slide? When you plug in the residual and you get a negative, when you're plugging it into that equation, when you do y minus the y residual,
No.
wouldn't it be 5 minus -2, which is
No. Y is 3 and y hat is 5. Y is the actual value.
oh
And y hat is the predicted value. So y minus y hat is -2. Get all of these numbers, absolute value them all and add them together.
okay, got it. Thank
Okay.
you.
So what we're going to do now is use a different line, which is not probably the best fit line because it kind of completely ignores those two. It just goes this way. But let's see what we get when we do this one. So according to this, what is the predicted value when x is 2? Whether it's this x or this x, what is the predicted value? What is the value on the line right above or beneath 2?
7.
7. And for this one here, what is the predicted value for an x value of 8?
5.
5. What is y minus y hat for this one?
-7, which is -4.
-4. 7 minus 7 is?
0.
5 minus 5 is?
0.
13 minus 5 is?
8.
Absolute value them and add them together.
12.
Well, so there you go. So there's your answer. We got 12, but then again, the points are right on top of each other. So I still don't know if it transfers to a more general case, but it certainly showed in this case that we get 12 no matter what.
Okay.
So this student's guess as to how we do it is still can't be right. Okay. So what we're going to do is kind of similar to the standard deviation, and we'll do it a little differently. We're going to take the squares instead of absolute valuing the residuals to get negatives. We're going to square them. So let's do this again. The same two lines. Hopefully you have them written down somewhere.
Yeah. The
What
first
was-
one is 5599.
5599, and the second one was?
-2. Oh, I'm sorry. The second
Okay.
order?
We can go in order too.
-2,
-2.
2, -4, 4.
And when I square the residuals, I get 4, 4, 16, 16 for a total of 40. And what were they in the second case?
They're 7755.
7755.
-4008.
-4008. Square them all and add the squares, and we get 80. Now, while the first way didn't work, this one clearly gives a smaller sum of the squared residuals to the line that we think is a lot better, right? So this is line 1. And in fact, this is how we do it. The line that we pick is the one that minimizes the squares of the residuals. In fact, that's what it's called, the least squares regression line. Okay, the method of least squares is this technique where we pick the line that has the lowest sum of squared residuals. Now, how many lines are there? In theory, there's infinitely many lines that we could be looking at. And how are we going to check them all? And the answer is you can't, okay? But there's calculus techniques which you're not prepared for or ready for. There are calculus techniques which can single out the unique line that minimizes the sum of squares. And there's formulas that are derived from said calculus. And when you use those formulas, it's actually pretty simple. Do they give me the formulas here or do we not bother? It looks like they don't bother. So lucky you guys. Okay, we don't bother to do it. We just know that it can be done. It can be done. So what are some characteristics of the least squares regression line? So it says using 2 points on the line, find the equation of the regression line that you drew in part D of the previous activity. Well, equation part D, that was, which, that's this one. Okay, so let's remind ourselves again. We draw it again. It was 5 and it was 9. And we draw a line through them. And the question is, what is the equation of this line? Well, to find the equation of the line using 2 points, what do we do first?
Don't you have to find the slope?
We got to find the slope first. How do we find the slope?
The y, the formula.
Yes, rise over run.
Yeah, rise over.
We rise from a y value of 5 to a y value of 9. That's a rise of 4. As we run from 2 to 8. So our run is 6. So the slope is 4 over 6 or 2 over 3. Do we agree?
Mhm.
Okay. Once we have the slope, what do we do next?
Don't we plug it into y equals mx plus b?
Okay, so we have y equals mx plus b. Of course, now I don't have to write the letter m because I know what m is, so I'm going to erase that.
We know B.
Do we know v? I don't remember learning it. How do we know b? I mean, at the end of the day, that's what we need to finish this.
Mm,
B is the y-intercept, right? Is that what we
Yes.
said?
Yes, it is.
But you said we can't extend the line back.
No, we can't use the extension, but we can still calculate the equation of the line. Whether or not that y-intercept has any physical significance is another question.
Oh,
But the line is still the line. So how do I find b? So the answer is pick a point. I don't care which point you use. Let's use this one.
oh yeah.
And let's plug in the x and y values. So y is 5 and x is how much?
2.
2. So this equation here must be satisfied. Because that equation is satisfied by every point on the line. If it's satisfied by every point on the line, then it's got to be satisfied by that point, for example. So what is 2/3 times 2?
4 over 3.
4 over 3. So if we bring that 4 over 3 to the other side, we get b equals 5 minus 4 over thirds. 5 over 3 is 15 over 3, so b is equal to 11 over 3. So the equation of the line, y equals 2 over 3x plus 11 over 3. Write that down. Well, actually, I can scroll down and keep it much lower where we're at right now. Here we go. Look at that. That fits perfectly. We'll just pretend it was there the whole time.
Professor, the bottom, is that 5 minus 4 over a 2? The very bottom to the right.
3.
Oh, 3. Okay, it cuts off.
2 over 3 times 2 is 4 over 3.
Okay.
Okay. So now we have the equation of the best fit line. Oh, why do I keep hitting that one by accident? There we go. Hopefully you copy that over so I can scroll down. I'll keep scrolling. Okay. So I need that line. So I'm going to erase this stuff. but I'm gonna keep the line for a bit. Oh, cool. Okay, so next question. What is X bar?
The mean.
Well, the mean of the X's, correct?
Mhm.
Because we're also gonna have a Y bar. So here are my X's again, 2, 2, and 8, and 8. What's their average?
10.
I don't think that's the average.
2 plus 2 plus 8 plus, oh wait, sorry, divide by 4.
Jeez. You even have a whiteboard you can do your work on, and you still can't get it right. Unbelievable. And what's the average of the Y's?
Wait, you wrote 5? Oh yeah, never mind.
Okay.
15, 18, 21, 28, 7.
7. Notice something, by the way. If you plug in 5 into my equation, what comes out?
Like the previous one we did.
Well, the one we just calculated. Best fit line, which is still here.
If you plug in 5 into what? Into the X?
Into my equation, yeah. If you plug in 5 in for X,
You
what is
get 10 over 3 plus 11 over 3, which is 21 over 3, which is 7.
that means that the point X bar, Y bar must lie on your best fit line.
Oh, that makes sense because it's the averages.
It's the averages of the X and the averages of the Y got to be on the line. That's one thing that we know to be true now. The average of the X and the average of the Y, that point lies on the line. So if you plot that point and you draw a line through it and you start rotating that line to try to get the best fit, you know, it can't be any other line. That line has to be on it. And okay. Now, something else to keep in mind, which is pretty cool. If you go back to the example way above here where we calculated these guys, if we did not absolute value them, but we just straight up added them, what do we get?
What page is that one on?
Slide 6 or slide 7. When we had these residuals, we absolute valued them and then we added them, or we squared them and then we added them. But if we didn't do any of that, if we just straight up added them, what do we get?
-4.
Oh,
plus
right. Yeah, go keep going. I'm sorry. I thought you were done. Go ahead. I'm sorry.
For the number 7 example, -4 plus 8, which is +4.
There should be 4 numbers though.
But there's 0, 0. Are you talking about the one that's on page 7?
This one here?
Yeah, the
Yeah,
ones that were 7, 7, 5, and the ones that came out were -4, 0, 0, and 8. So -4 plus 8 would be +4.
Let's do that again because that shouldn't work. Why do I keep hitting that? That
Can you
shouldn't work.
repeat the question?
Huh?
Can you repeat your question?
I'm asking what these 4 numbers add up to before we absolute value them.
Before you absolute value them, it's -4008. So that's 4.
I understand the issue. Not for that one, for this one. The best
Okay,
one.
I was like, wait a second,
Yeah,
what am I
yeah,
doing
Not for
wrong?
that one. I'm sorry.
So -2 plus +2 is 0. It would have been 0, wouldn't it?
It would have been 0.
Yeah.
That's another property of the best fit line. The sum of the residuals of the best fit line is 0.
Got it.
Which is apparently not true if it's not the best fit line. Okay, as we just saw, because I'm like, wait, it should be 0. What is going on here? So, yes. Okay. So the sum of the residuals is always 0. That's the second feature. We're not going to worry about the details of this problem. Just those are the 2 things that you should know about the best fit line is that 1, it has to go through the average of the X, average of the Y. That has to be on the line. And the sum of the residuals have to be 0. So question, what's the slope of this line here?
3.
3.
3.
Hopefully that's not a shock. 3. What's the slope of this line here?
Negative 0.3.
Negative 0.3. What's the slope of this line here?
0.6.
0.6.
How much?
15.
15.6.
15.6. So in general, the slope is always the coefficient of what?
X.
Of x. The slope is always the coefficient of x. Now, when you have the equation of the line, it's kind of easy to find the slope because you can just read it. If you have the line itself graphed, how do you find the slope? You find two corners
Mm-hmm.
because you want to make sure that the line goes through corners so you know exactly the numbers. You can't use random places because those are approximations. You do the rise, 1, 2, 3, 4, up 4, over 2, 4 over 2. So the slope here is equal to 2.
Yeah.
If I do this one, I have a corner right here. I got a corner right here. Down 3 and to the right 1. What's the slope?
Negative 3.
Negative 3.
3.
This one here, I find a corner. I find a corner. Up 2, 1, 2, 3, 4, 5 over 5. What's the slope?
3 over 5.
1, oh, up 3. Whoops.
Up 3 over 5. Yeah.
3 over 5. Yeah, let's undo that. And write it again. 3 over 5. Okay, so that's, how to find the slope if you're given the equation and how to find the slope if you're given a graph. The question is, how does the slope, or what does the slope mean on a regression line? When we said, for example, way back at the beginning of class, that the handspan was negative 5.6 plus 0.4 times the height, the slope here is the 0.4. It's the number in front of the variables, number in front of the heights, okay? But what does that mean, the slope is 0.4? That means that my rise over the run has to be 0.4. If I go 0.4 up, I have to go 1 over. Well, what does 0.4 up mean in the context of this example? And what does 1 over mean in the context of this example? If I go to the right by 1, what am I talking about? What's happening?
You're going
Here.
1 inch.
I'm gaining 1 inch in height.
Yeah.
And if I go up 0.4, what does that mean in this example?
Your handspan increases by 0.4 centimeters.
Exactly. So the slope in this context is the following. For every 1 inch gain in height, my gain in handspan is predicted to be 0.4 centimeters. For every 1 inch in this direction, I predict 0.4 centimeters in this direction. So for every 1 inch gain in height, I predict a 0.4 centimeter gain in handspan. Does it actually happen? No, there's always randomness in the world. That's the way the world works. But it is my prediction. Does that make sense?
Mm-hmm.
I hope it does. That's it. Oh no, there's more. What's this?
There's like 3 pages left.
Oh man, I thought we were done. I was so excited. All right, let's see if we can skip that. Research consistently has found a negative correlation between math achievement and math anxiety. Right? The more anxiety you have, the worse you perform, even among young children. This scatter plot shows the results from a study of 2nd and 3rd graders in San Francisco area. It says higher scores in the YAT2 indicate higher math achievement. That's my Y. Higher CMUS scores indicate more math anxiety. That's my X. The regression equation is this. And R, don't forget what R is, negative 0.66. Negative 0.66, that's like moderate, right? This is not a very strong correlation. It's moderate. But the slope is negative 0.5. As a fraction, what is negative 0.5?
Negative
Half.
Negative 1/2. Remember
Yeah.
what that means? If I go down 1 here, the rise is 1. If I go down 1, I go over 2. Correct?
Mm-hmm.
So for every gain of 2 points on my CMOS score,
Mm-hmm.
I predict a loss of 1 point on my Y at 2 score.
Mhm.
Right? And therefore, for every 1 point increase in math anxiety score, if I go 1 to the right, the predicted math achievement score drops by how much? If 2 to the right drops 1, then 1 to the right drops a half, or 0.5, which is, of course, the actual slope. And what does each point on the scatter plot represent?
1 score.
1 score, right? 1 student, 1 score. Well, not 1 score because there's scores for both of them. I would say 1 student is a better answer because it incorporates both scores, right? There's 2 scores going on here. Agreed?
Mm-hmm.
Right.
Okay. 1 student's math anxiety score is 20 points higher than her friends. How would you predict that their math achievement would compare? If one's anxiety is 20 points higher, then what do you think her math achievement would be based upon the line we just drew?
Lower.
By how much? That's the whole point of the slope. The slope is a prediction. If I go 20 to the right, I go down by how much?
10.
By 10, right? 2, 1, 20, 10, just it's a multiple, right? Negative 1/2 means it goes down by half. If it goes to the right 20, it goes down by 10. Interpret the intercept of the line. The intercept is 130. That means if a student got a score of 0 on the CMOS scale, she would score a 130 on the math composite score. That's the prediction, right? The y-intercept is when the x value is 0, correct?
Mm-hmm.
So the prediction is that if a student scored a 0 on this scale, she would score a 130 on this scale. Of course, you might say, this doesn't look like 130. 130 is here. But again, remember the scales are off, right? So you can't go all the way, okay? So a student whose math anxiety score was 0 is predicted to have a math achievement score of 130. Does this study show that higher math anxiety causes lower math achievement, or could it be the other way around? So remember, statistics is not about causation. Statistics is about correlation, right? Causation comes from common sense. Correlation comes from the math. We can't say anything about causation. We just know that they are correlated. Maybe there's an underlying lurking variable that we don't know. And I don't want to do this one, so we're done. So are there any questions on today's lovely section on regression? It was really lots of fun. I can tell by your immense participation across the board.
I have an off-topic question.
Huh? Yes, go ahead.
Do we have class on Wednesday?
What is Wednesday that I wouldn't? Remind me?
It's Veterans Day. Sun gives it off.
Message today saying that we do not have school on Wednesday.
Who said that? Who said that?
Me. Hi. I got a message saying that we don't have school on Wednesday because of Veterans Day.
This is the greatest news ever. Well, no, this is horrible. I'm not going to see you guys on Wednesday. That's horrible.
We discussed it last week. How did you forget?
I don't know.
Let me pull it up. Just
yeah, pull it up. Let's be sure.
No,
There's
it's
like a text
I confirmed
message.
that today too. My other classes have been canceled because of Veterans Day.
This is wonderful news. This is wonderful. Not that I don't want to see you guys, but to be honest, I don't want to see you guys. So this is great.
That last message. Oh, it's backwards for you guys.
Oh, okay, sorry.
No, we can see it the right way.
Oh, on mine it's reversed. I don't know why. But
Yeah. You can fix that by setting your video to mirror my video, and then it'll look the right way to you, and it'll still look the right way to us.
Oh, I didn't know that.
Yeah.
Sick.
This is great, guys. This is wonderful.
Day off. Woo.
Wonderful.
My message said the next 2 weeks. I don't know if I got the right one.
Let me load up something. Hold on a second. CSUN.
Oh wait, but I have a message saying it's like a whole
calendar,
month now.
20. Hold on.
The rest of the year.
This is fall
What?
2020, right?
School's done forever? What?
Wait a second.
More school? What?
Wait a
What?
second. Yeah, it
We
says
all get
November,
free
November
degrees?
11th, Veterans Day holiday, campus closed. There we go. No school.
Day off. Woohoo.
Hey.
Guys,
More
I will
like
miss you.
I
I will miss you. I will shed tears of sadness that I'm not going to see you Wednesday. Or tears of happiness. I don't know. I don't know until it happens. It's hard to say, but I will see you guys in a week. So have a wonderful, wonderful everything.
Wait, Professor, this is our last chapter? Chapter
No.
16?
No,
What?
no. I gotta upload more chapters.
Yeah,
It goes
didn't
like-
you hear? We're done.
They're done.
Oh,
They're giving us.
I'm
They're
sorry.
giving
I
us
didn't realize we were done.
They're
Oh,
giving us the rest of November and December off
that would
as
be awesome.
for this horrible year.
That would be amazing. No, there's more chat. I just haven't uploaded them. I uploaded like 5 or 6 of them like about a month ago or so.
Oh.
Okay.
So I gotta
Can you
upload
do that
them.
ahead of time again?
Review.
Say again, who, what, where, when, why, what?
Can you upload them all again so that I can print them out ahead of time?
Yes, I will
Thank
put
you.
that, I'll put that on the agenda for the week
Thank
after
you.
everything else that I have to do.
And the homework solutions, yay.
You want the homework solutions right away?
Hell yes.
No, you gotta at least have time to do it without solutions.
No.
Friday.
Yes, yes. At least a few days.
All right.
All right, fine. All right. Well, anywho, then I will see you all.
Monday.
Enjoy your vacation, guys.
Bye, Professor. Thank you.
I will.
Thank you.
Bye.
You're welcome. You're welcome. You're
Bye.
welcome. Anyone still here? Brianna, you there? Oh, I'm still recording. When did that?